Of course. Okay, so thanks for the invitation, of course. So let me be brief on the introduction so that we have more time for discussion, okay? So this is a workshop on generative networks, right? So in particular on graph generative networks. So let me briefly present the status of the MPP HEP group, which is these people here, on our work with message passing guns. So next slide, please. I obviously don't need to tell you that in the LHC, we will always have hadronic jets, right? And usually how we do that is matrix element, hadronization, simulation. Simulation is either GNN for full simulation or some flavor of a parameterized simulation. And then you could make a trade-off in between accuracy and speed and where you want to sit on this curve. So the million-dollar question is literally, can we find new places in this parameter space which are based on machine learning? So the proposal here is to do the generation of hadronic jets using a generative neural network. And there are many possible applications to this depending on what you want to train on. For instance, if you train simulated jets, then you can learn better simulation. And in principle, you can substitute fast thing. But if you want to dream at a higher level, you can train on real reconstructed jets and make the network learn the whole thing, better hadronization, better simulation. Heaven's the limit, right? So in the next slide, I also don't need to motivate this, right? You know better than anybody else. There is a gigantic jump coming our way for the high luminosity LHC, both because of the luminosity and the high granularity detectors. And one key thing that we have noticed before is that the data that we're going to get, they are a good match for the graph architecture descriptions because they are irregular geometry. They have irregular geometry. For instance, in the CMS HZCal, which is mostly a prototype of what we are going to show in this talk, and they are intrinsically not ordered. So if you put the two things together, you see that it's natural to use graphs, which is good because they are semantically much more powerful than regular arrays like images. And you see that there is a lot in the line, right? Because of this big jump here, generation, simulation, and digitization is something like 30%, according to the latest CMS projections. So next slide, please. So in excruciating detail, the generation, simulation, digitization, and reconstruction of events with jets, and therefore of jets in CMS, and I suppose in Atlas is going to be the same, is given in this diagram on the left. So the goal is to try to substitute some or almost all of these steps by a generative model. So with this introduction, let me talk about a proposal, which is particle cloud generation with message passing guns by Hansal et al. I'm also going to describe the neural network that we invented, and also the standard data set that we have prepared and proposed as a benchmark for further studies. Next slide, please. So this is a quick refresher. And I don't know if this has been said before, but a quick refresher on generative adversarial networks, GANs. These were proposed by Goodfellow back in 2015, I guess. So the idea is that you have two neural networks that they are playing what's called the zero-sum min-max game. There is a big loss function down there and the idea is that you train two networks, one against the other. So you have a generator G that learns the data distribution, and then when it's trained, it can generate samples of whatever you want to generate from pure random noise. And then on the other hand, you have the discriminator D that tries to estimate the probability that the sample it is seeing is a real or generated sample. So the idea is that when you train the two in tandem, the two things will hopefully they will converge. And in the end, you have a good discriminator but the generator has become so good that it cannot fool the discriminator anymore. So in that sense, the generator has learned how to generate new samples. This is a very good, very successful idea, and there is plethora of examples. For instance, here is a generated cat from the These Cats Do Not Exist website. And I'm sure that you can find many others in the internet. For the next slide, please. So our idea then is how to create these neural networks here. And here is the key insight that I want to draw attention to in this talk. If you want to generate jets, you have to take the jet as a whole. The high-level jet features, they are global. Now, with this thing in mind, this leads immediately to some design choices that we made for the message passing gun. First, we do not have to construct the graph in a sense. We always use the fully connected graph architecture, and that's good enough for us. And then we build the neural network with message passing algorithms. So you aggregate the input of the whole graph, and then you use that to compute a function of the whole thing. And you never separate particle by particle. You concatenate all of the particle features or arrows, again, to try to preserve the global structure of the jet. Remember, the high-level jet features are global. And then in order since even though it's an unordered structure, there is some sense of history in there, right? Because the particles that you see in the jet, they come from the hadronization and the particle shower. So in a sense, there is a history of development of the jet. And we try to capture that by doing a residual connection to the previous particle features. Taking all this English into mathematical definitions, you have that n particle at a given iteration. N particle cloud at a given iteration. Each particle has a set of features, and then you define the message passing algorithm there, where these functions are implemented then as simple multi-layer perceptrons with 3 fully connected layers. If you go to the next slide, please. This basic idea you have to apply then to both generator and discriminator. Now, this is the idea, of course, but you have to set up some standard benchmarks to measure yourself against it. So, first, for our generator, which is this message passing gun, we are trying 2 approaches. You either directly generate the particle cloud with whatever n particles and L random features, or you try to simply generate a z-dimensional latent vector. So we steal this idea from the variational autoencoder world, and then use yet another fully connected layer to expand to the n times L dimensional matrix that will represent the particle cloud. And then these we have to pit against some other generators. And here are some generators, Argon, Trigun, and GraphCNN that we chose as our benchmarks. For the discriminator, on the other hand, we take as baseline the point net mix approach, which has a symmetry function in order to take care of the part of that the data set is unordered. It does some segmentation in order to combine local and global information. And then it has special characteristics that help ensure the symmetries. For instance, the particle cloud that represents a jet has to be invariant by rotation and translations. And then for the discriminator, we either use that or we use again a message passing gun, just like the generator. And now I'm sorry that I just noticed that I never said, but yes, the plan is to use particle clouds to generate to represent the jets. So it's a step beyond image. And again, it's kind of natural because, as I said, it's unordered and no hierarchy. If you go to the next slide, please. This is again this is just a picture of how the network goes. So again, you have the particle cloud on the left. You do the message passing part in in the second column. And then this is a generated particle cloud. You'd go and do and compare with a real particle cloud. You have the discriminator, which again is a similar architecture. In the end, it will spit out some hidden features where we do an averaging pool, a fully connected layer, and a final output that tells us if it's real or generated. And then you train this whole thing using the min-max game I just described it previously. In the next slide, please. Now we have to know how we're going to measure if this thing is doing its job well or not. So let me talk very briefly about metrics. We have, in general, two approaches to metrics in our paper. Either we take some from the computer vision field, which is widely used to evaluate the three-dimensional object point clouds. We either use the minimum matching distance or the coverage. The coverage is the only one that has the larger, the better. Okay, so just so that we keep that in mind. The technical definition here, the minimum matching distance of two data sets. Let's say X is real, Y is generated. You do a matching. You match each element in Y to the closest element in X, and closest means the smallest energy movers distance, and then you average over that. If that's small, that means that the generated set more or less describes well the real set. So if you minimize the MMD, you're ensuring the quality. On the other hand, the coverage is a fraction of matched elements in Y. So if you manage to maximize your coverage, that means that for the maximum amount of particle clouds that you generate, you will always be generating something that is different, but looks like a real jet. So it ensures the diversity. For the next slide, please. Another metric is what we invented in this paper. They call it Frechet particle net distance. And what's the Frechet particle net distance? Is something that we derived from the Frechet inception distance, which is for the famous inception V3. So what's the idea? You calculate the Frechet distance in between real and generated samples. The definition of the Frechet distance square is there, but you calculate it in between Gaussians fitted to the activations of the fully connected layer of the network. So in the inception distance, you calculated on the last layer of the inception V3. In our case, we calculated on the final layer of the particle network. So you calculate this, and once again, this is sensitive to quality and diversity. But the key thing here is that since you're using the last layer of the network, this already directly measures the high-level features. So if you go back, let's say 3 slides to the diagram, please, slide 8. You see here exactly. You see here the fully connected layer on the right. So we fit Gaussians there to both real and generated and calculate the Frechet distance. And there you want to minimize. Back to slide 10, please. And then directly next slide. And finally, the Wasserstein first distance, which is again a mass moving distance. And this is again physics inspired because it's very close to what we do when we compare data and simulation, which I don't think I need to explain this much. Here we calculate the Wasserstein distance in between high-level distributions of the real and generated jets. We choose for our high-level features: relative eta, relative phi, relative pt, and relative jet mass, which are good. I mean, it's exactly what we want to read. We want the distribution of our jets of our generated jets to follow the real ones, but it's not absolutely obvious that we want to that these are all the needed high-level features. So the alternative, as was even discussed by Savannah previously, is the energy flow simulation. energy flow polynomials, because they are like in particle energy correlations. And it can be shown that they are basis for infrared collinear safe jet observables. One thing that I want to draw your attention here is that this thing is conceptually equivalent to the Frechet particle net distance, because both are in high-level features, while the computer vision things, the MMD and coverage, they focus more on the low level. But the key thing is that the Wasserstein is things that we know, right? It's the relative eta, relative phi, so it's things that are interpretable. So let's go to slide number 12, please. Let me briefly speak about the data set. We are using the GNN data set that we're proposing as a benchmark for late CZ studies. We have three classes, blue on top and light quark, and more or less 150,000 jets per class. We have two versions of the data set, one with up to 30 particles per jet and one with up to 150. This study that I'm showing you here is up to 30. And then the key thing here is up to something. And of course, some jets have less than 30 particles, and the idea is that we mask for the missing particles. For the data set, it's essentially an N34 frame, where the four features are the eta, phi, and relative PT, and the mask. If it's masked, it's all zeros. So you have there an example gluon jet as a projection of a particle cloud. And to make things easier for everyone, besides publishing the data set in Zenodo, we also publish the GenNet library that has these evaluation metrics that I just talked about, infrastructure to access the data sets easily, the loss functions, so on and so forth. So we have the networks, we have the metrics, we have the data set. Slide 13, let's talk about the results. So for the light quark jet, you see there you have the real, and in different colors you have the MP gun, so in blue, in green the fully connected, in brown, it looks different for me, brown you have the graph CNN, and in yellow the tree gun. And I think the results, if you look at the distributions, I think the results speak well by themselves. If you look at the metrics instead, you see that we have many more on the paper, but let me just showcase the following. If you use either fully connected or graph CNN or trigon with PointNet, you have not so good results when compared with if you use the message passing gun with the message passing gun as discriminator. But if you see on the paper, you see that you can mix and match. You can use the MP generator with the PointNet discriminator or any generator of the discriminator. And then, if you look at the paper, you will see that all of these results are not good either. The only thing that really blows everybody out of the water is message passing on both sides. You see there the W1M is the Wasserstein distance for the mass, the average for the other features, the average for the 5 first energy flow polynomials, the Frechet particle net distance, the covariance, more is better, that's what the arrow means, and the minimum matching distance. And you see that message passing is best in all the cases. Depends a bit on the flavor, but you see that in between the two of them, there is not much difference. Then if you go to the top quark jet from slide number 14, please, you see that again, it's the same case with some interesting other things. First, you see that the trigon and the graph CNN, they completely fail to describe the relative particle PT. And why is that? You look at the big spike on the left, it's the mask. They cannot learn the masking. if you look at the relative jet mass, you know that the top quark, it has the two peak structure, right? When the top is fully merged, on when it's W fully merged plus the big quark. And you see that the only distribution that is on top of the red is the blue, so it's the message passing. All the others fail to describe the structure of two peaks. And again, for the jet energy flow polynomials, you see that again only the message passing has the correct structure. You can see on the table also again that the message passing is the best in all cases, except for the W1 distance for the features. But you see that there the difference is not so big. You look at it's 1.6 plus or minus 0.4 to be compared with 2 point something. So not that bad. Slide number 14, please. 15, please. Some remarks. Remember that the end goal of this thing is to have a conditional gun. So of this we cannot, of course, escape. We have to condition on what's the parton, what's the PT of the parton, and what's the type. All these results that I showed you are for partons of 1 TeV-PT. And these are already said, but the message passing gun outperforms the baseline model that chosen almost every metric, with the caveat that you have to take the pair as a team. It's pointless to try to use one generator with a different discriminator. For the light quark jets, we managed to successfully use the masking strategy and teach it to the MP gun. And for the top quark jets, we saw that only the MP gun managed to catch the bimodal structure. So in slide number 16 is the conclusions and outlook. As you have seen, as I have tried to tell you, the high-luminosity LHC data, they are a very good match for graph and graph neural network approach. High granularity, very sparse, irregular geometry, and intrinsically unordered. This is literally made to fit for graphs. And we believe that using generative models can solve the simulation apocalypse that computing apocalypse that's coming on our direction. We know that reconstruction is going to be also problematic, but even more problematic, but simulation will still be 30%. We cannot just ignore it. We believe that the guns are a frontier of research, and we propose the message passing gun to simulate this high energy jet. We show that it can learn at a very high level, both the high level features and the substructure. I hope that I was clear enough and still on time for some very good discussion. Thanks. So, questions, comments, criticism?
Let's see if there is some questions from Zoom first. Okay. I see Daniel in the room. Why don't you go first?
Yeah, okay. So thank you very much. This is really, really cool. And yeah, I remember reading the paper, and it's just like a masterclass in following this all the way to the end. And yeah, really amazing. Two little questions. One was, as I recall, one piece of the puzzle that you didn't quite crack in the paper, I wondered if you had made progress, was where the nodes come from in the first place. I think you ended up like sampling from a distribution. Is that right? And is that still how you do it?
For the number of particles.
Right.
Right. So yes, we're still sampling from the distribution. We still haven't cracked up that one.
Okay. I guess that's the part of the question I'm curious about, because I'm sure people are interested in doing this for tracking. Like, can you generate a whole event? 100,000 nodes. Where do those nodes come from? can you see that there is a path to using this kind of network to generate a whole tracking event? Or do you think that maybe there need to be other problems solved before we get to there?
I think it's at this point, I think it would be a little bit premature because generating the whole event would, right? I mean, even if you generate all the jets, but as soon as you have to add, I don't know, pile up an underlying event, I think everything goes the way of the dodo. So in principle, it should be possible, but I think there is still a lot of road in front of us. It's premature to even speak about that in my mind.
Maybe a question which is a little follow up on this one. So in your model that you generate for the jets, you said it's a sparse model. So I imagine you start with the nodes and which are the particles, then you make it fully connected, essentially like a fully connected graph. So how sparse are the weights of the edges of the connections?
I think I didn't explain myself well. What I meant with sparse is not the sparseness of the graph itself. It's the sparseness of the data. Is that what I meant by sparse? It's like when you say that, oh, in the tracker or in the calorimeter, in the HG or the calorimeter, most of the sensors do not fire, right? Occupancy is very small. That's the sparseness that I want to draw attention to. The graph is in between the particles themselves at the end. We connect every particle to every particle.
Yeah,
that graph, I don't think it's sparse.
Oh, you do not think it's sparse? Okay, so
I don't think so.
It's really like a dense model, like a language model, in which all the pieces are okay, talking to each other.
Yeah, as far as I know, that's it.
That's a difference with tracking, of course, which is sparse also in the sense of the edge.
Exactly, I remember that. Yeah, because in tracking, of course, the most heats are not connected to all the other heats, are only connected to the next one. It's a different meaning of the sparseness that I'd say.
Yeah. Yeah.
Let me add one question, and for picking up what Daniel said. When you generate a downstream feature such as a chat that depends on an upstream feature, which is what happens in the tracker, and you are not generating the upstream part, how would you make sure that the event consistency stays correlated, but these correlations stay somewhat preserved? You see what I mean?
Kinda, yes. So
like imagine you push the tracking simulation still through J and due to how the dice falls, you're needing pion showers hadronically in the tracker. So your input assumption of a 4-vector particle to your gun is already wrong. Did you think about something like this?
Let me see if I can translate the question to what I think I understand, and then I try to answer. First, Paulo, if you can go back to the slide of the diagram, exactly, jet simulation is cruciating, the diagram number 4, I guess. Exactly, the excruciating detail. So the question, I think the question is, but Thiago, you have, for instance, suppose that you are doing part of the trajectory simulation there in still on Giant, instead of substituting all the steps, you only want to do the rest of it in with the generative network. I think that if you it's not that it's all or nothing, but if you train a network that wants to start from hard process, from Parton, PT in eta phi and the nature and what kind of Parton it is, you do a network for that. You cannot mix and match. Oh, but let's say that's also there is also trajectory simulation done on the side of Jant. That I think it's not easy to do, and I don't think it would make sense. But if instead of starting all the way up there in the hard processes, you say, oh, let's start with the trajectory simulation and the calorimeter simulation part and use that as input for the generative network. Then, of course, and by input, I really mean, oh, let's train the gun to start from that part. There, I think it's possible, yes, but it's not obvious. It's not obvious that you can mix and match.
But that's what we in Atlas developed as the ISF, which is the integrated simulation framework that makes sure that the fast simulation, calorimeter fast simulation, which also the gun setup, starts at the handover boundary between the detectors in order to mitigate this. But it makes your input, of course, way more difficult. So instead of having physics 4-vector inputs from your partons, you can sometimes have already a shower input into your shower gun. Yeah?
I guess it depends. Sorry, depends also what you want to do.
Sure.
If you want to do detector simulation, you have to do what you say. But if you want to do, correct, if you want to unfold your detector effects, you can also go from the original form momenta of the art scatter to whatever are the reconstructed form momenta that you see in this detector, and forget about the fact that you have even a detector. I mean, you are basically learning what the detector does without simulating.
Yeah, but the problem, this is correct, but my point was that if you don't do the full detector with one learned simulator, but you can do two different ones, then you decorrelate your event. If the simulator B doesn't know what simulator A,
but that's why you have the graph.
We had exactly this problem in the Atlas Fast 1 simulation or whatever, Fast Carlo Sim 1 simulation, where whether it's a generative model. At the end, a shower parameterization is also a generative model, but a poor man's one, put it that way. You draw a random number in a simple way, parameterized one for the calorimeter response, which is uncorrelated from the simulator that does the tracking simulation. So you could have your tracker simulation could have a catastrophic energy loss event, and your gun in the calorimeter simulates something completely different because it hasn't known anything about the catastrophic energy event. So that's why you either define handover boundaries, I think, which makes it difficult because
you're still thinking about the detector simulation, and I agree, but the detector simulation is true. I'm thinking more something like that, right?
There also, if you do jets and tracks uncorrelated, you have a problem.
I mean, you could say, okay, I have my initial core, then I have my Parton, then I have my hadronic jet, electromagnetic jet, and then I have this thing which I call a pion or an electron, right? And so each one of those is a node. You can have it fully connected or partially connected, but there you have the message passing to make sure that if you lose all the energy in the electromagnetic calorimeter, then the other calorimeter has to look right. In principle, I'm not saying that it's easy to do in principle. But yeah, if you go to the detector level. Anyway, it's nice to talk about stuff, and that was the purpose of the workshop, but I think we need to move on.
Thanks
And-
everybody for the opportunity of speaking here.
And thanks, Tiago, and sorry if you were pressed for time, but
No, no problem, no problem. I'm still on time. Thank you very much.